So a base is a proton acceptor. It gets hydrogens or gets H pluses. Lots of times we drew it in chapter 4 like a capital B for base, put some teeth on here, give it a big eyeball, and this one is an H plus getter or a hydrogen eater. You can give him some little arms right here and some tiny little legs to run around on, and he's the evil base monster. He's a proton getter. The strong bases are lithium, sodium, potassium, rubidium, and cesium, and calcium, strontium, barium hydroxides. Notice they're on the periodic table in the shape of a B like this. And then remember that these guys right here have a +2 charge, so they have 2 OHs in them as well. So these are the strong bases. You memorize those. You know which ones they are. They split up completely. They ionize completely. They dissociate completely. When split up, they're an excellent source of hydroxide ion, and hydroxide ions are a great acceptor of H pluses. If you draw the hydroxide ion's Lewis electron dot structure, it looks like this. Brackets around it, little -1 out here. And you can see that there's lots of unshared pairs of electrons around this O, and so therefore it's really good at attracting things without electrons, like H pluses, who have no electrons, obviously. Here's an example reaction, KOH, reacting or being placed into water. The KOH then completely dissociates because it's a strong base. Reacts with the water. This OH right here is a really good getter of hydrogens, so water donates a hydrogen to it, and we say that this is a proton acceptor. On the right hand side then, this would become water, and this would become OH over here. So that's how those strong bases act basic, by getting hydrogens, in this case from water. So bases have an OH group on them, for the strong bases anyway, and some weak bases do as well. You remember that the calcium, strontium, barium have 2 OHs, making them doubly dangerous. But what happens if they have no OH group and they're a base? Well, then many of them are what are called amines, A-M-I-N-E-S. Amines, of course, are an organic group, and an amine is a single bonded to an NH2 with an unshared pair of electrons where hydrogens are attracted. This unshared pair right here is very attracted to H's or H pluses, especially when something acidic is around or water is around, because this wants to get attached to another H plus if it can. One of the simplest types of, quote, amines, unquote, is something called ammonia. Ammonia is NH3. It doesn't have a carbon in it like an amine would, so it's technically not. But it does have an unshared pair of electrons, just like this, and this is where these come from. And this is a weak base, but still a good acceptor of protons. Here's here's an amine, another base. This one is C2H5NH2, and we talked about drawing Lewis dot structures last time. And if we draw this Lewis dot structure, we would first have a CH3 group, or I'm sorry, yes, a CH3 group, and that would take care of 1 hydrogen. Then we'd have a CH2 group that would take up 2 more hydrogens right here, adding up to 5, so therefore the C2H5. And then we have the NH2, so N bonded to 2 H's with an unshared pair of electrons right here, and this would be the area that would be basic and would be a good acceptor of protons or acceptor of hydrogens. So let's talk about drawing carboxylic acids and amines, because amines show up quite a bit, and so do carboxylic acids in terms of weak acid and bases. So this is butanoic acid. But, of course, means 4 carbons. Oic acid means that it's got the C double bond OH to it. So the suffix tells you that it's an acid. And we know that it's got a C double bond OH on it. It has a carboxylic acid group. Carboxyl group. That's many whoops, I missed an X there. carboxyl group or a carboxylic acid group. I'll write this correctly. Carboxyl group, YL. This is called a carboxyl group right here. Since it has the prefix but, it means it's got 4 carbons. So we'd have a series of 4 carbons, 1, 2, 3, 4. On the first or the last carbon, we would have a C double bond O, and then we would have an O connected to an H. And this would be our acidic hydrogen, or the one that would be given away. And of course, off of each one of these carbons right here, we'd have hydrogens to saturate it to make sure that each carbon has 4 total bonds around it. So there's butanoic acid. Here's the quick way to draw it. I think you learned this 2 video casts ago. So carbon to carbon to carbon to carbon, a double bond O, and then we'd have to put an OH like this off of the end, and then this H right here would be the acidic hydrogen, or the one that would be given away in an acid-base reaction. How about amines? Well, in amines, you have a prefix as well, propyl, meaning 3 carbons, and then amine, meaning that we have an NH2 group on it, an NH, unshared pair of electrons on it, like that. So we know it's got a CNH2 on it. The prefix means that we've got 3 carbons. So we'd draw 3 carbons in a row, and then we'd have an NH2 group on the end or the beginning of it. So NH here, and then we'd have hydrogens saturating these carbons, of course, to fill it up, so each carbon would have 4 bonds completely. This would be the basic portion of the molecule, and if these two were reacting together, the hydrogen would be given away here, it would be accepted right here, and so we'd end up with a negative charged species right here. This thing you'll find out once it releases its proton, it's called the conjugate base. And this, once it accepts its hydrogen right here, would have a positive charge, and it would be called the conjugate acid. Learn more about that next video cast. Here's the short way of drawing it. I've got to put a couple of hydrogens off of here, off of the nitrogen, and you can see there's 1, 2, 3 carbons, 1, 2, 3 carbons like this. All right, how about some reactions with Lewis dot structures in acids and bases? So here's the first one. First, assume that they're aqueous. When in doubt, react the acid or the base with water. When in doubt, react it with water. So here's a reaction of CHOOH. This would be called meth, because there's only one, and then oic acid, so methanoic acid and water. So here's our methanoic acid, C double bond OH, and an H off of the carbon right here. That's this H. This would be the hydrogen that would be given away, and then here's the Lewis electron dot structure of water. We're giving away this hydrogen to water. On the right-hand side of the reaction then, we would have the water gaining a proton, so we'd end up with H3O with a positive charge. Notice how I put brackets around it, with a little plus sign, and we'd end up with this with one less hydrogen, and it has to be this oxygen that's missing the hydrogen. Remember this C to H right here can't give away that H because the polarity just isn't strong enough for it to be giving it away. It's not acidic. The arrow shows where the acidic H moves. So notice how I drew this arrow showing that the hydrogen moves over to here. Here's the second one. Ethylamine dissolves in water. So ethylamine would be 2 carbons, 1, 2, and then we'd have an amine group, NH2, like this, 1, 2. And then we'd be reacting it with water, and let's draw the water like this, HOH, and then we can put an arrow. We know the hydrogen would be donated to the base right here because the base is a proton getter, and so on the right hand side we'd still have our ethyl group, the nitrogen group, and now we'd have 3 hydrogens stuck on that. Since it's got a hydrogen, it's going to have a positive 1 charge, so we put it in brackets with a +1. The water right here has lost a hydrogen, so what do we have left? An H connected to an O, and that would have a negative charge. Notice we made some hydroxide, and that was one of the very basic, simple definitions of acid, is things that create OH- are bases. So let's do another example here of methylamine and water. Here's methylamine, methyl and an amine right here. Here's water right here, gives away the hydrogen. This makes the methylamine with an extra H, and so they call this the conjugate acid, and then they'd call this the conjugate base because it's left over of what the acid has after it gave away its hydrogen. More on those two terms in the next video cast. The base here, the acid here, the conjugate acid and the conjugate base right there. If you look backwards, you can see why it's called the conjugate and the conjugate. If you look at this direction, you can see that this acts as a base from here to here. It gets a hydrogen. And so instead of calling it just the base, backwards base, they give it a fancy name. They call it the conjugate base. And if you look from here over to here, you can see that the species containing carbon and nitrogen loses one hydrogen. And so it's called the acid because it's a donor of hydrogens, but in the backward direction, so they call it the conjugate acid. Fancy names: conjugate acid, conjugate base. The word conjugate is just a fancy way of saying the backwards or the opposite direction, or what's left over after the acid-base reaction has taken place. So here's just two more reactions. Here's ethylamine reacting with ethanoic acid. So ethyl means 2. Amine, of course, means it has an NH2. So here's my ethylamine. Reacting with ethanoic acid. So here's my 2 carbons, C double bond OH. I neglected to draw the dots on here, but you can just remember that they are. And then, of course, it's going to give away this acidic hydrogen to the base over here. And so on the right-hand side, we're going to have those 2 carbons and the nitrogen with 1 more hydrogen and a positive charge. And then we're going to have this with 1 less hydrogen right here, and it will have a negative charge. This would then be called the conjugate base, and this would be called the conjugate acid, because this would be giving away a hydrogen from this side to this side, and this would be gaining a hydrogen from this side to this side. So backwards, it would be called conjugate. Here's one more example. Hydrofluoric acid solution reacts with methylamine solution. So hydrofluoric acid is HF. Methylamine, meaning 1 carbon amine. So 1 carbon, and then we've got an amino group right here, NH2. This H right here. Arrow, arrow. And then on the right-hand side, the hydrofluoric acid would give away the H, so you could draw the arrow here showing where the hydrogen would go. And then over here on this side, we just have F with a little minus sign. And we would have the carbon connected to 3 hydrogens. And then it would have an N with 3 H's around it, bracketed, and it would have a positive sign now. So another way of drawing these lots of times is instead of C with 3 H's around it, they'll just write CH3 and then NH2. Don't get confused by that. Just be okay that, oh yeah, that means C with 3 H's around it. So there's a couple of examples of acid-base reactions with big scary looking bases, big scary looking acids, and knowing that the hydrogen is donated to the base. And then you even learned a little bit about conjugate acids and conjugate bases, which you'll learn more in chapter 16.